Yeah, okay, so welcome back, everyone. So today it's our pleasure to have Alain Celisse, who will be talking about early stopping for reaching optimality while saving the computational resource. Yeah, thank you, Alain.
So thank you, Boumediene, for the invitation. And hello, everyone. So when Boumediene asked me to make a talk, I decided to discuss this question about early stopping because I think it's a nice topic to work on this time. And especially I will discuss, let's say, early stopping applied to gradient descent mostly, although what I will say is absolutely not limited to gradient descent. So I will start with a shorter introduction with the statistical framework I will consider. So I'm considering a regression problem where I'm working in a fixed design situation, meaning that my observation corresponds to some random variables which are independent, which are cappers, xi, xy, x1, y1, until xn, yn, which follow the regression model you see on the screen. So yi is equal to a regression function denoted by f star, evaluated at xi plus a noise term epsilon I. So as usual, in a regression problem, the regression function f star, which is simply the conditional expectation of y given x, is unknown. And the main goal in what follows is to estimate f star. Our assumption in what follows is that we assume the error terms are independent, they are centered, and they are sub-Gaussian random variables. So the epsilon I are sub-Gaussian random variables. And also the main assumption, perhaps, which corresponds more or less in this domain to the state of the art, is that we assume the noise level sigma to be positive, but on top of that to be known. So as soon as I have this model, I've just introduced to you earlier, we can use the matrix vector notation that I will repeatedly use in what follows. So bold y, the vector y, corresponding to the coordinates y1 to yn, is equal to f star, the vector, which corresponds to the evaluation of the regression function f star at the x1 point until xn, plus the vector of noise term epsilon. In what follows, what I will try to do is to estimate f star by means of a reproducing canonical Hilbert space. I mean, by means of functions within this space, which will be the space which will contain my candidate function for approximating f star. And so it means that I'm given or I choose a reproducing kernel denoted by k at the bottom of the slide, which is a positive semi-definite, which corresponds then to a reproducing kernel, which can be understood as a kind of similarity measure with specific properties. And as soon as I've chosen such a PSD kernel K, then I'm given a reproducing kernel Hilbert space, calligraphic H, as you see. And then as soon as I've done that, it gives rise to the classical Gram matrix, capital K here, which is simply the matrix of the evaluation of all pairs xi, xj for all cappers ij between 1 and n. So it's an n times n matrix. And I will consider the normalized Gram matrix Kn. So it's K divided by n, the sample size. So at this stage, what I can say is that I choose the kernel K, and this choice will, as it's written on the slide, will encode the amount of smoothness of the function f star I'm trying to approximate. So this choice of K is not made for free. It's because indirectly it encodes some smoothness assumption I will make on f star. As soon as I've done that, then now I need a criterion for choosing, let's say, a good estimate for f star. For doing that, I consider the empirical risk, so denoted by omp of f, which is the average over the observations of the discrepancy between yi and for a candidate function f and corresponding vector capital F, the difference between yi and fi squared and average over all observations. So this is my definition of the empirical risk of the function f, because I recall you that the vector f, capital F, is actually equal to the evaluation of the function f at the observations, the locations x1 to xn. So here it is. I insist on the fact that further along the talk, I will use the notion of nth norm denoted in this way, which is simply defined as you can see on the picture on the slide. So as I'm given now a criterion for measuring the quality of the function f for approximating f star, I will use it, meaning that I will define my best candidate, let's say for approximating f star, as one minimizer of this empirical risk over the space calligraphic H. This is possible. And the choice I make in what follows is to approximate this f hat, to compute an approximation to this f hat, let's say, by means of gradient descent. Meaning that actually I will simply, using the reproducing property, which is classical in the reproducing canal framework, I can show that this empirical risk as a function of f is actually differentiable, meaning that I can calculate its gradient. And then I come up with the gradient of the empirical risk evaluated at ft, and it gives rise to the classical update rule for introducing the gradient descent algorithm, meaning that if I initialize the process at, let's say, the null function f0, which is 0, I can simply iterate ft and calculate ft plus 1 from ft minus a given step size alpha t plus 1 divided by 2 times the value of a gradient of the empirical risk at ft. So this is really classical. And this is what I will consider in what follows. I insist on the fact that I can evaluate now, this is a sequence of functions, because for each iteration t is here my iteration number. For each iteration t, I come up with a function ft, or ft plus 1, which belongs to the RKHS by construction, precisely because the gradient here is an element of the RKHS calligraphic H. So ft is an element of the RKHS, and I can evaluate this function ft at the locations x1 to xn, and this gives me the vector capital Ft, which is simply coinciding with the value of function ft at x1 until xn. This capital Ft vector has or enjoys a closed form expression, which is written on the slide, which makes this quantity a linear estimator, so namely a matrix times the vector observations y, bold y. Okay, so this is what I can say until now about the gradient descent. You will see how I can use it in what follows. And just before introducing the first important idea of the talk, I need, let's say, to introduce what is called the generalization error, also called the risk of the function ft, which is defined for new observations, which are copies of the previous one, so xi, yi prime, which is an independent copy of xi, yi. I can evaluate the expectation prime over these new observations, so the ability of the function ft for predicting what happens at the location xi given a new observation yi prime, on average over all observations, because I'm working in a fixed design situation, meaning that here I only take the expectation over the noise epsilon prime, which is underlying this couple of random variables. And now I think since I have this risk, this measure of quality for measuring quality of ft, I can display this picture where I simply draw the value of the excess risk. The excess risk is defined in this way. So the difference between the risk of the function ft and the risk of f star, which is the quantity I'm trying to estimate. I can access to this quantity on simulation experiments, and this is exactly the message I want to deliver here. I'm doing simulation experiments, and I can compute this excess risk, and I display this excess risk as a function of t, the number of iterations. What I can see is that this excess risk is sharply decreasing as the number of iterations increases at first. So you see a very sharp decrease, meaning that there is a strong improvement in the quality of FT as I make a few first iterations. Okay. After some time, if you iterate more, you see that I'm reaching a kind of local minimum for this curve, which displays the value of the excess risk. And after some time, you see that it starts to increase again. And if I further iterate, then I see that now the curve seems to stabilize, and actually it's completely flat, and I do no longer gain anything in iterating further. And the question is, what does it mean? It could seem somewhat counterintuitive, perhaps for some of you, but actually it means that along the curve, there exists a number of iterations at which I can reach the best possible performance along this path of iterations. And if I further iterate, so if I make too many iterations, then actually the statistical performance is worse than what I got after only, let's say, 12 or 13 iterations. So actually, it suggests that in practice, I should not iterate too much. I should interrupt the process of computing iterations as soon as I can, because if I do that, if I make too many iterations, then I worsen the performance, which is exactly what I want to avoid in practice. And this is all the more the case as if you iterate too many times, if you worsen the performance, then you waste some computational resource, which is exactly what you want to avoid as well. This is what you get on this instance for gradient descent in the context I was describing to you earlier, but actually it's absolutely not limited to gradient descent because you can observe similar curves if you're optimizing using an EM algorithm or something like that, or very similar algorithms to gradient descent. So it's very general phenomenon, which is absolutely not limited to gradient descent in regression. But this is the main focus I will consider in what follows, nevertheless. So as I told you, it means that too many iterations will worsen the performance, and it suggests that, on the contrary, I should interrupt as early as possible this iterative process, meaning that I want to introduce an early stopping rule for saving time and computational resource, and while achieving an optimal performance, because ideally I would like to be able to stop as close as possible to this optimal number of iterations. So this is the goal we pursue in what follows. And now I finish the introduction part, and I will discuss with you I will introduce step by step a few notions I need to explain what's going on exactly. So what I want to emphasize is that I've started the talk by discussing gradient descent algorithm, but actually, as I suggested earlier, what I'm talking about here is absolutely not limited to gradient descent algorithm. And actually, in this work, we have considered a broader class of estimators, which is called a class of filter estimators. I will define that in what follows. And after spending time on filter estimators, I will introduce an early stopping rule and or key ideas, let's say, about early stopping rules. And I will turn to introduce the first stopping rule, for which I will provide some basic analysis and also optimality results. And we will see that the results we have, if I'm teasing a bit, are optimal in some range of smoothness for the regression function we are trying to estimate. But if you are outside of this range of smoothness, then unfortunately the first stopping rule I will discuss is suboptimal, and then we'll introduce a means to improve its performance, which will lead us to a new stopping rule, which is based on smoothing. This is what I will detail in what follows. And after that, if I have time, I will discuss results expressed in random design, because, as I said, I'm working first in a fixed design situation, but after that, I will move to the random design setting as well. Okay, so I did not say that from the beginning, but of course, if you have any question, then don't hesitate interrupting me. Don't wait until the end for asking any question. I will be very happy to try to answer. If no question, then I can further introduce the last notations of this talk, mostly, I need two ingredients in what follows. The first one is what is called the evaluation operator, which is simply nothing but the operator Sn defined on the Hilbert space with values in Rn, which corresponds to, for a given function f in the Hilbert space, the evaluation of this function at the locations x1 to xn. So Sn of f is simply this vector. And if you remember what I was saying from the beginning, because I'm working in a reproducing kernel-based space, I enjoy this reproducing property, which is nothing but this equality, namely f of x1. You know that by definition of the reproducing property, it's equal to the scalar product within the Hilbert space, calligraphic h, between the function f and the evaluation function kx1. And this is the same for all xi's. As soon as you have this evaluation operator, Sn, then I can define its adjoint. The adjoint Sn star of this operator Sn is defined in this way. So you take a vector u in Rn, and the operator Sn star evaluated at u is only the average or the coordinates of u, so ui's, times the evaluation k of function kxi. So these are two ingredients I need in what follows. For introducing some formulas, I will detail in the next slide. And what is interesting, if you're not already aware, is that actually these two operators are already connected with classical quantities. For instance, the normalized gram matrix I introduced earlier, so the ratio between the gram matrix K divided by N, is actually equal to the composition between this Sn star operator times Sn, or composed with Sn on the left. If you introvert the two operators, then you come up with the classical empirical covariance operator, sigma n, which is Sn star composed with Sn. So you have these two operators, Sn and Sn star, which are key ingredients, and they are naturally related to key quantities, namely the normalized gram matrix Kn and the empirical covariance operator sigma n. Okay, now, since I have this ingredient, I can introduce the more general class of estimators for which what I will say in the following applies. So this is the class of filter estimators, Ft. So Ft is defined from a given function gt, which is called the regularizer. And for instance, if I give you an example, if you choose this function gt, so the regularizer in this way, so for a given step size alpha, then the estimator you get as a result is nothing but the gradient descent iterate after t iterations, ft. So this, for a particular choice of the regularizer function gt, you get the expression of the gradient descent after t iterations. But it's even more general, because if you make another choice of gt, which is this one, so very simple function gt, then what you get is simply the Tikhonov regularization, or the estimator for a given value of the regularization parameter 1 over t. You get the kernel, because we work in a reproducing kernel-based space, kernel ridge regression estimator. So always VT, also FT, and so on and so forth. You can, by let's say an appropriate choice of a regularizer function GT, you can get numerous classical estimators such as Showalter estimator, iterative Tikhonov regularizer, and so on and so forth. So there are lots of different estimators which enter into this particular framework I'm talking about now, which is the one of spectral filter estimators. So what you have to keep in mind is that these spectral filter estimators are completely characterized as soon as you make a choice for GT. And you see from this formula, once you have chosen GT, you apply this function GT at the empirical covariance matrix operator, sigma n. You compose that with the adjoint of the evaluation operator, so Sn star, and you apply that to the vector y, and you get a function within the Hilbert space, which is for gradient descent, the TIF iterate of output by the gradient descent algorithm after T iterations then. Okay, so this is a nice framework because it's very general to some extent, and it allows me to now apply, let's say, a given machinery to this family of estimators, and in the same time, I will be able to derive results for a lot of estimators.
Alain?
Tell me.
Yes. You introduced the function GT as something that takes inputs in R plus.
I'm sorry, I can't hear you properly. Can you speak louder, please? I'm sorry.
You introduced the function GT as a function taking inputs in R plus.
Yes. Okay, this is a notation. It means that you're asking me what is the meaning of this notation, right?
Yes.
Okay, actually it means that you can define for any operator applied to a function space, which is properly defined, blah, 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 which is the case for this one, which is compact, let's say, such that you have kind of diagonalization, which is possible, let's say, a spectral theorem for it, which is the case for sigma n. You can define this notation GT of sigma n as being the evaluation of function GT at the eigenvalues of the operator sigma n.
Functional calculus then, okay.
Yes, exactly.
Okay.
And,
does it answer your question?
Yeah, perfectly.
Okay.
Alain?
Yes, tell me.
You didn't cite the work of Rosasco about spectral filter estimators. You refer to that as well?
So the paper they have produced recently about spectral filter estimators and optimal rates is something they have produced, let's say, recently compared to the work I'm talking about. But I agree that this is the same family of estimators.
Yeah. Okay. So it's
yeah. And sorry.
No, I wanted to know if you extend for instance, the statistical guarantee to more general cases, or.
So I'm sorry, but I can't hear you properly. I was hearing guarantee and.
Yeah. Sorry, I'm going to. I don't know where No, I was thinking, about the work of 2007 by Rosasco, Very, about the study of these spectral filter estimations. And I think that you extend the scope a little bit in your.
So
I want
okay.
to know how you. I mean, is it exactly the same framework, or you extend it a little bit?
Okay. So I'm sorry, I can't hear properly, but what I understand from the remark after that, you can, okay, we can discuss about that independently, is that there is a previous work by Rosasco and his team, and I agree. The thing is that usually in their derivation, what they do is that they define such a class of functions, so the same as mine, for instance, and they derive upper bounds for the approximation error on the one hand and estimation error on the other hand. And after that, since they have two upper bounds, which depends on a parameter such as t for me at the moment, then they are trying to optimize the two upper bounds as a function of t, and they get the best possible upper bound, and they get as byproduct a kind of best choice of t, given some assumptions on the class of function, let's say some smoothness assumptions on the target they're trying to estimate. So it gives them, as long as I understand what they have done, it gives them some ideas of the optimal dependence of t, the number of iterations, or more generally the parameter, with respect to inferential parameters of the problem, such as the smoothness of the function they are estimating, the decay of the eigenvalues in the RKHS, and so on and so forth. Do you agree?
Yeah.
Okay. So this is a different spirit, the kind of thing I'm talking about. But because it's too early in my presentation, it's only the 7th or 8th slide, and actually you should wait, I think. And if it does not answer your question, then if you do not see any difference, then tell me.
Perfect. Thank you very much.
Okay, so this is the class of estimators I'm considering. And then the question is, how to choose t. So, and in particular, what I want to do in what follows is deriving a strategy for choosing t, which is completely data-driven, which is the first main difference compared to precisely previous works by Rosasco and co-authors or other people in this area. So just to make it clear how you can embed the Tikhonov regularization or kernel ridge regression in this framework, you have here the classical optimization problem giving rise to kernel ridge regression. It turns out that if you define this function lambda, f lambda as one minimizer, as the minimizer of this problem, and if you choose lambda as a function of t, you come up with a situation where you want to okay, the key thing you have to decide to choose is the value of lambda. In what is made here, you assume that this regularization parameter lambda depends on t. You assume that you're given a kind of grid of values for lambda, which depends on t, and you will go through this grid of values of lambda. So when t equals 1, let's say you consider lambda 1, which is the largest possible value of lambda within the grid you have chosen beforehand. And after that, the second, and you see this problem as if you wanted to choose the optimal value of lambda within this grid of values, but by starting from the largest one and step by step decreasing the value of the candidate value for lambda. And you want to interrupt this process, this iterative process, as early as possible for avoiding having to compute the estimator, the kernel ridge estimator, at a value of lambda, which is useless because it is suboptimal in a way. This is the main message I want to deliver here. And then in this respect, you can embed this kernel ridge regression question in this early stopping framework I'm trying to describe to you now. Okay, so let's have a look at the excess risk I was talking about. Earlier, I said that the excess risk as a function of the iteration number is decreasing as I'm iterating a bit. And after that, it slows down, it reaches a local optimum, and after that, it increases again. This is exactly what is displayed here. You have to look at the red curve, which is the one of the excess risk. You see that it decreases sharply at first. After that, you slow down, you reaches this global optimum, and after that, you worsen the performance as well as you iterate further. If you want to make the classical decomposition in terms of Bayes term and variance term of the excess risk, which is made here, you come up with the Bayes term, which is the first one in green. And if you display its behavior on the picture, you see the green curve, which is decreasing as a function of t, the number of iterations. Meaning that, okay, you can see on this example that as you iterate further, it means that the Bayes of your estimator output after t iterations of gradient descent is decreasing. And this would be the same if you're doing what I was explaining with kernel ridge regression as well. On the contrary, if you think about the variance term, Vt here, capital Vt, the red curve, sorry, not the red curve, the yellow curve, I'm sorry, the color is wrong. The yellow curve, you see that at the beginning, it's almost zero, it's very close to zero, and after that it increases, and actually it always increases, and it slows down, and it reaches a value like a kind of a horizontal asymptote. And that gives you an idea of the classical behavior you can expect. Actually, as you will iterate, it means that the Bayes will decrease, and actually we can prove that the Bayes is decreasing as a function of t in this machinery, in this context I'm describing. And on the contrary, the variance is an increasing function of t in our context. And this explains why there is this kind of U-shape, more or less, curve I was describing for the excess risk curve, meaning that it sharply decreases because at first it's very close to the curve of the Bayes, and after some iterations, the Bayes is so small that now the excess risk curve coincides more or less with the variance curve, which is the yellow one. And this is what you see on the picture. So it explains that actually, if you want to be optimal in a way in your choice of iteration number, then you have to balance Bayes and variance, which is what we want to do in what follows. Okay, so I explained that and already. So I will skip this. The only thing I want to mention here is that, as you see on the picture also, the bias and the variance curve are crossing each other by construction. And you can imagine that you have a T which is continuous, because it's possible to extend to this framework as well. So, and in this case, you have continuous curves, and they necessarily by construction cross each other. I don't want to enter into details, but it's obvious in the picture, so I think you are convinced more or less. And the other ingredient I need is this one. Actually, I introduce the bias term VT, the variance term VT, capital VT, and actually in what follows, I will also consider what I call the proxy variance, small VT. And you see the difference between the two things is simply that the proxy variance is an upper bound on the variance term, and simply you, in short, remove the square on the GT of kn quantity within the trace. And this is completely expected because the eigenvalues of kn, GT of kn, are simply sandwiched between 0 and 1. And this is why when you square them, you get something smaller. Intuitively, this is what happens. And this is why you have this upper bound, which is quite nice. So now everything is in place to allow me to introduce now early stopping in more detail. So this is what I will do now. So as I said, you have, at each iteration, you compute an estimator, let's say by gradient descent, you iterate. This is what we have made here. And honestly, the only thing you have access to is the empirical risk value. So you can evaluate from the data the empirical performance of your estimator after T iterations. This is what we do here. We draw the value of the empirical risk, the black curve, as a function of the iteration number. So you see that this curve is decreasing. And you have to keep in mind that at each iteration, the question is, should I stop or should I make an additional iteration? Because you want to interrupt the process as early as possible. This is the goal at the end. So here, okay, the empirical risk decreases sharply, let's say. You iterate further, it still sharply decreases. Should I stop or should I iterate further? This is the question. It's not clear. You iterate further, and you see that the curve slows down once again. You get something, the empirical risk value, which is very close to 0 here on this example. And after that, okay, it's very flat, and it's more or less it sticks to 0. What can we do? You should stop somewhere, because probably here it's too late. So you need a criterion based only on the empirical risk to make a choice based on the empirical risk, to decide when to stop. This is what we do here. But one important ingredient in the reasoning you have to keep in mind is that due to the constraint we introduce by considering the problem of should I make a further iteration or should I stop, we introduce a change compared to the classical way of thinking about this model selection problem. Because usually people compute all candidate estimators, let's say until capital T, and after they have computed all these candidate estimators, they come back and they try to decide which one among the candidates they have computed is the best one, according to, let's say, a penalized criterion or cross-validation or anything you want. But here, it's completely forbidden because you don't want to compute all candidate estimators for throwing away most of them. You want to stop as early as possible. And due to that, the originality of the problem is that you cannot reach the performance of the oracle. The oracle iteration number is simply the one which minimizes the risk value or the excess risk value currently. You cannot, in full generality, achieve this oracle performance because precisely if you are unlucky and if you are limited due to computational constraints to only perform capital T iterations, then if you are unlucky and if the oracle iteration number is after capital T iterations, you will never see it. So you will never reach the same performance. So in full generality, you cannot compare, you cannot hope to reach the value of a risk, which is similar, which is the same as that of the oracle. So it means that we need another, let's say, number of iterations which will serve as a reference to compare our performance to the best possible performance we can achieve. And this is the rule of this reference stopping rule denoted by T star, which is not the oracle one. It's something else I will introduce now. T star will play the role of a reference stopping rule, which is kind of the best stopping rule we can try to mimic at some point from the data, given the kind of machinery I'm trying to describe here. How can I define the stopping rule? T star, so the reference stopping rule, by simply introducing a trade-off between bias and variance, as I already said earlier. Actually, you know that if you want to achieve kind of minimax optimal rates when they are available, then you know that this is possible only if you have kind of balance between bias and variance. Otherwise, it's definitely not possible to achieve such rates. So the natural idea is to say, I will define the reference stopping rule T star as the first time at which the bias, which is a decreasing function of T, will become smaller or equal to a variance, which is an increasing function of T. Because the two curves are crossing each other, this is something I already pointed out earlier, then it makes sense. It's possible that sometimes due to limitation, computational constraint, you will never see T stars. So in this case, okay. I'm not saying that they always cross each other at a finite and reasonable number of iterations, but this crossing time does exist. So you can calculate T star, the reference stopping rule. And the good news for us in the context I'm describing here is that, fortunately, the performance of the reference stopping rule, which is not the same as that of the oracle stopping rule, is nevertheless close to the best possible performance, so that of the oracle. This is made explicit by this inequality I'm showing to you here. You can prove by exploiting monotonicity assumptions about the bias as a function of T and the variance term as a function of T. We can prove that actually the performance of the reference stopping rule T star is actually sandwiched by the best possible performance of the oracle. On the left, clearly, because this is the oracle performance, so you cannot beat it, of course. On the right, you only have to pay a factor 2, meaning that, okay, it's true that the reference stopping rule can be worse than the oracle stopping rule. This is possible in full generality, but you will never lose more than a factor 2 in terms of performance, which is nevertheless quite nice. And this allows us to compare the best performance of the, let's say, reference stopping rule to that of the oracle. In particular, because I have in mind that in what follows, I will derive oracle inequalities, and for this reason, this is the previous result is really helpful. So as long as you trust me regarding the previous notions I introduced, then now I will introduce the first data-driven stopping rule we will discuss in what follows. As I said, the only thing you have at hand at each iteration is the quantity, which is the empirical risk of the output of your grand descent algorithm after T iterations. So the empirical risk of T. And you see that this curve is unfortunately decreasing. The question is when to stop. And the idea is to say we could, and this is the discrepancy principle, we could stop as soon as the empirical risk becomes small enough. Small enough means smaller than a given threshold. And the question is, of course, what is the value of this threshold? And according to the heuristic, which is more or less suggested here, the threshold is very simple. It's sigma squared, the variance of the noise terms. And we can prove, theoretically, this is what we will do just after, that this works in practice. What is the reasoning? Intuitively, although there are some, let's say, bizarre, the intuition is that if you are at an iteration T such that the estimator you get Ft is very close to the value of the function f star you are trying to estimate, then you're expecting that the residual y minus ft should be very close to y minus f star, meaning that if t is almost optimal as number of iterations, then you're expecting that the expected value of the empirical risk, so this is what is written here, should be not too far from sigma squared. This is an intuition. This is absolutely not rigorous, but fortunately, if we introduce our stopping rule in this way, meaning that we will stop at the first time t at which the empirical risk becomes smaller than the variance of error terms, then we can prove rigorously that it works in practice. And this is what we will do just after. So this is not the first time people are doing that. This has been done in other contexts for other family of estimators, but here it was the first paper where it was established and analyzed in the context of reproducing kernel bud spaces. So now, if we turn to the analysis, theoretical analysis of this stopping rule, which is very simple, I insist on the fact that, and this answers the previous question, I think, here, absolutely, I'm not interested in trying to optimize t as a function, so the upper bound on the variance term and on the estimation error, and jointly as a function of t, and defining the best possible value of t, depending on some assumptions I make, and so on and so forth. Here, it's not what I'm doing. I'm defining, on the contrary, stopping rule tau dp, which is fully data-driven. As long as you trust me that, or you accept the assumption, let's say, that sigma squared is known, then since you can compute from the data the empirical risk value, then you have everything at hand to be able to compute tau dp and choose in a data-driven way the optimal number of iterations. So optimal, it's a bit ambitious because I've not proved anything yet, but still you can calculate it. And this is what we will see in what follows. Okay, so a few ingredients. First, I will simply tell you that we can calculate the expectation of the empirical risk to have an idea of the average behavior of the empirical risk as a function of t. And you can prove that on average, the empirical risk as a function of t minus sigma squared is related to the bias and variance and proxy variance in following the equation which is written at the top of the slide. So, of course, if you forget the last term, you see that the expectation of the empirical risk minus sigma squared is exactly equal to the sum of the bias term plus the variance term. So if you forget the last term, it would be exactly equal to the excess risk value. And then if you were optimizing t, so optimizing the empirical risk as a function of t, then it would make a perfect job. But unfortunately for you, the empirical risk depends also of the last term minus 2 times vt, which is also increasing as a function of t, the proxy variance. I recall you that vt, small vt, is an upper bound on capital Vt. And this is typically the term which is responsible for overfitting. For instance, if you are simply trying to define t, the best value of t as the one which minimizes the empirical risk value, you see that because the empirical risk is a decreasing function of t, you will come up with the largest possible value of t, for sure. And precisely this is due to this last term, which is the last one, the big one compared to capital Vt. So we have to make a further step. Otherwise, we are done. How to correct or to take into account the trend to overfitting of the empirical risk, which is already known, and this is not new. You can sandwich the expectation of the empirical risk minus sigma squared expression by precisely two terms, two quantities, and you see that these two quantities on the left and on the right of the inequality are very close to each other. The bias minus the variance on the proxy variance on the right, and the bias minus 2 times the proxy variance on the left. So in a way, you see that this is interesting because it means that this difference between the expectation of the empirical risk and sigma squared is some kind of balancing between the bias and the variance. And this can be made more precise by saying that, for instance, if you remember the definition of the reference stopping rule, T star, you know that T star is the first time at which the bias becomes smaller or equal, but equal because we are working with continuous quantities, is equal to a proxy variance. If we define the reference stopping rule in this way, then it means that precisely at this reference stopping rule, we know that the right-hand side of the inequality is exactly equal to 0. Because it's exactly equal to 0, it means that at this stopping rule, T star, you know that the expected empirical risk minus sigma squared is negative or non-positive, meaning that you are already below the threshold, meaning that you are in the situation where the expected empirical risk is already smaller or equal to sigma squared. On the contrary, if you're defining t as tau dp, and if you are willing to assume that the expected empirical risk is close to the empirical risk itself, then by definition of tau dp, which is the first time at which the empirical risk becomes more or equal to sigma squared, then you are in a situation where this term is approximately zero, meaning that at this position, precisely for this number of iteration tau dp, you are in a situation where the bias is already smaller than twice the proxy variance. So you see that these two stopping rules, tau dp and the reference stopping rules, are actually create a connection between the difference between the empirical risk and sigma squared on the one hand, and on the other hand, between the bias and the variance terms. So this is very nice, and this is a property we will exploit in what follows. So now my goal in life is deriving an oracle inequality. This is typically the kind of inequality which is expressed at the top of the slide. It means that I will calculate the excess risk of my estimator evaluated at tau dp, and I want to prove that the performance of this estimator at the data-driven stopping rule tau dp is almost, up to a multiplicative constant c, the same as that of the oracle. So the best possible performance ever along the path of the estimate successive iterates ft, plus a remainder term compared to the performance of the oracle, which is noted here in a generic way, Rn. This is the kind of inequality I want to derive. How to do that in this context? First, you have to remember that I said that thanks to arguments owing to the monotonicity of a bias and variance term, I'm able to prove that the performance of the reference stopping rule, here you have to notice that I consider ft star. So this is the performance of the reference stopping rule. It's not worse than twice the oracle performance. So it means that for deriving a comparison between the performance at tau dp and that of the oracle, a sufficient condition is to be able to relate the performance at tau dp and that at that of the reference stopping rule ft star. First thing. The second thing is that now, this is what I explained here, how to relate these two quantities. And the first step is to say, okay, we'll simply and brutally, I would say, upper bound the performance at tau dp by twice the bias term at tau dp on the one hand, and twice the proxy variance term at tau dp on the other hand. So it means that now we only have, for answering our question, to quantify the behavior of a bias term at tau dp on the one hand, and the behavior of a proxy variance at tau dp on the other hand. And the main tool I use to do that is deviation inequalities, such as Hovding or Hanson-Wright inequality and things like that. If you do that, if you use these tools, concentration inequalities in general, this is the kind of thing I'm using, then you are able to prove such a result for tau dp. I'm sorry, I modified the notation. It should be tau dp here. What does it tell you? So I recall you that the only assumption we are making is that at this stage, we assume that we have sub-Gaussian random variables for the error terms epsilon I. This is the only thing we are using here. And also that the kernel is bounded. I did not write it here, but it should be written. The kernel is bounded. These are the two things we are using at this stage. As long as you use these two properties, then you're able to prove that for any t larger than t star, so the reference stopping rule, then tau dp with, let's say, high probability cannot be too large compared to t star. In other words, tau dp with high probability cannot be larger than t for any value of t larger than t star. And the level of probability with which this should be true is controlled precisely depending on t, and the upper bound is written here. You have twice the expectation of the exponential of minus n, the sample size, times c, a constant, which is simply a numeric constant. I don't care about its particular value, times the minimum between two terms. And the interesting thing is that these two terms are depending on the proxy variance, let's say on the variance. the difference between the variance at t and the variance at t star. What does it mean? It means that when, let's say, okay, as t will be larger, because t is constrained to be larger than t star, but assume that t becomes larger and larger, then because vt is increasing as a function of t, vt increases as well. So you have here the difference between vt and vt star, which is positive by construction, which is increasing as a function of t. And then it makes the global probability smaller and smaller. And the rate at which this probability will decrease is completely driven by the variance of by the variance term, vt. This is what it means, which is very nice. And we have also similar property for the bias term. I'm not written here for the sake of, let's say, space, but actually for saving space, but actually this is the same. Same story for bias term. Thanks to such result, then we are able to quantify what I was explaining. So the proxy variance, I said that earlier, that for deriving my oracle inequality, I need to relate the proxy variance at tau dp to what happens at t star. And this is exactly the main merit of this result at the bottom of the slide. If we make the same assumptions, sub-Gaussian error terms and Gaussian and bounded kernel, sorry, then you can prove that with high probability, you have that the variance term at tau dp is controlled with high probability by the proxy variance at t star, plus a deviation term y, which controls more or less, which is related to the level of control of the probability of the event. This is exactly a byproduct of this previous oracle deviation inequality I was commenting on at the top of the slide. So this is why there is a connection between these two things. It's perhaps not obvious because I'm going quite fast, I recognize. So perhaps, it's not obvious, but you have to keep in mind that this second result is actually a kind of corollary of this proposition at the top of the slide. So this is exactly the one goal we had. We are able now to say that there exists an event with high probability that is completely controlled, such on which the proxy variance at tau dp is controlled by the proxy variance at t star, which is exactly what we were looking for. And we have the same result for the bias, meaning that at the end of the day, we come up with this oracle inequality we were looking for, which tells you that there exists an event with high probability controlled by u, such that the performance at tau dp is comparable with the performance of the oracle plus deviation terms. The value of the deviation terms depends on u, which controls the probability. What you see is that, there are two terms, and the limiting one, I would say, in terms of rates, depending with respect to n, is the first one, 1 over square root of n, which is the rate of these additional terms. So what you can claim at this stage is that as long as you are in a situation where you are expecting that the rate of convergence of the oracle is slower than 1 over square root of n, then for sure this oracle inequality is optimal, meaning that the discrepancy principle rule, tau dp, makes a perfect job, because you have this oracle inequality, which tells you that tau dp is optimal, and these additional deviation terms are negligible compared to the performance of the oracle. So, full stop, I would say. But unfortunately, there exist situations where, on the contrary, you know that the rate of convergence of the oracle will be faster than 1 over square root of n. And in such a situation, clearly, these additional terms are suboptimal. So this is why we will turn to a modification of a previous stopping rule to come up with a new one, which is based on smoothing and which is optimal in terms of rates. And this is what I will explain in a while. So, formally, what I want to emphasize is that there are two big scenarios I can consider. There is a kind of hard learning scenario in which you assume that implicitly that the function you are estimating is not smooth. What does it mean, not smooth? It means that the function you are trying to estimate is outside of the reproducing candidate space you have chosen to make the estimation. It's so far from the RKHS that the rates you can expect in such a situation, which is a very bad situation, are slow or slower than 1 over square root of n. And then in this case, tau dp is optimal. But on the contrary, if you are in an easy learning scenario, meaning that you know that f star belongs to the RKHS, then you know that in such a situation, you can expect fast rates, meaning fast rates faster than 1 over square root of n. And in this case, you need something more because tau dp is suboptimal. And this is the kind of situation we'll consider in what follows. So if we come back to the empirical risk, we have to analyze the reason why it generates these suboptimal rates, which is 1 over square root of n. And one reason for this suboptimality is that the empirical risk suffers the fact that if you look at the decay rate, so the spectrum, let's say, of the normalized gram matrix, Kn, you remember that we are in a reproducing canary bed space, we can compute the gram matrix, we normalize it by 1 over n, and we draw the ordered eigenvalues of this Kn matrix. And we see that actually these eigenvalues are very large for the first ones, the largest ones, and after that they sharply decrease. And after only a few of them, very quickly, most of them are non-zero, but still very close to zero. This is kind of bad conditioning of the gram matrix in a way. And then it means that you suffer this bad conditioning of the gram matrix, normalized gram matrix. And this is one reason for which the empirical risk exhibits this fluctuation of order 1 over square root of n, which are suboptimal for tau dp. So how can we modify this? The idea is smoothing the residuals. What does it mean? It means that we are suggesting to multiply the residuals y minus ft after t iterations by a smoothing matrix, capital L, which has an operator norm which is smaller than 1, okay? And in our case, we have made a particular choice for this smoothing matrix, but a priori, you should not be limited to this choice, but this is a choice we have made for illustration purposes, let's say. And we have chosen to use as a smoothing matrix Tikhonov regularization with parameter of regularization, which is 1 over capital T. I will come back to the interpretation of capital T in a while, but still, I can do that, let's say, and provided I do that, then simply, thanks to the multiplication by this matrix, the smoothing matrix, I will kill, in a way, the influence of very small eigenvalues, which are responsible for these bad fluctuations of the empirical risk, roughly speaking. Okay. So actually, in this new framework, I can reproduce exactly what I was doing earlier, meaning that thanks to this smoothing matrix, I have access to a quantity which is the smoothed empirical risk. I can compute it from the data at each iteration, no problem. In principle, I can do so. And then I can apply the same machinery I was explaining to you for designing an early stopping rule, which is data-driven, but this time I will base my stopping rule on the smoothed empirical risk, and so this one. And then the new stopping rule is this one, tau SDP, where you recognize that I use the smoothed empirical risk, and now I do no longer consider the variance sigma squared, but now a kind of updated variance value, which is now sigma squared times the trace of L transpose, L divided by N. You see that in addition to this choice, it arises in the expression of tau dp precisely capital T. The capital T is exactly the same capital T as the one which is introduced in the smoothing matrix here, in the regularization. What does it mean? It means that this capital T can be understood as a kind of emergency stop, meaning that, for instance, you know for computational constraints that you are not willing to make more than capital T iterations. At most, this is the price, the computational price you're willing to pay. Cannot pay more. And then if, unfortunately, the empirical risk has never become smaller than a given threshold, which is this one here, then after capital T iterations, then you stop the process and you output capital T, because this is the best you can do given the amount of iterations you are willing to pay. So this is the way you can interpret this. And for illustration purposes, I can say that if you compare the value of tau dp over, let's say, a few repetitions, let's say 100 repetitions, you can display the histogram of the value of tau dp, so the former stopping rule. And on the same experimental design situation, you can compare the value of tau dp to that of tau sdp, so the new stopping rule, on the same experiments. And now you see that in the first situation, there were a lot of realizations on which I was choosing tau dp almost equal to 500 iterations. Now it's no longer the case. It happens sometimes, but most of the iteration number I will choose by tau SDP is now around 100 and 150 iterations, meaning that clearly you see that the variability of a stopping rule is lower thanks to the smoothing I've made. This is the main merit of this smoothing step I introduce. So now, okay, I take a kind of shortcut because I see that I'm almost, the time is over already. So I apologize for that. I will finish immediately. What I can say is that thanks to this new stopping rule, I get a similar oracle inequality, which has been updated now, because now you see that I do no longer have a 1 over square root of n rate for the additional terms. On the contrary, I get a 1 over n, but now the novelty is that I get as well at the numerator a square root of what we call the effective dimension. The effective dimension in the context of reproducing canal space is really known as the nice quantity to look at for quantifying the geometry, the difficulty of the complexity, let's say, of the RKHS space that you use to make the estimation problem, to solve the estimation problem. So in particular, the main merit of this quantity is that it depends by definition of the decay rate of the eigenvalues of the normalized Gram matrix. And then it gives you the opportunity to take advantage of the fact that the decay of the eigenvalue will be so fast that the trace can be very small, although you are working in a very high dimensional space in principle. And this is why you can inherit, thanks to that, a rate which is faster than 1 over square root of n. For instance, if you do not use any knowledge on the decay rate of the eigenvalues, you come back to the worst case rate, which is 1 over square root of n. So this result coincide with the former one in the situation where you do not take advantage of this effective dimension thing I was talking about. Okay, we can prove, thanks to kind of change of norm lemma, that we can translate all the results we have for the fixed design to the random design setting as well. Not for free, but it's possible at the price of some technicalities. And we can prove that in both situations, we are rate optimal, meaning that if you're in a hard learning scenario, you get the best possible rate over some class of functions. You're adaptive, really adaptive. And the same story in a easy learning scenario where you assume that function f star belongs to the RKHS, then you come back to you're adaptive for very smooth classes of functions. So we are optimal to this respect. And I stop there, and I thank you for attention and possible question. I will be happy to answer if any. Thank you.
Okay, thank you very much. Any questions or comments?
I hope it was not too fast or too late, or both of them.
It seems that people already asked their questions. All right, seems that there is nothing. Any other comments or questions from the audience in the room? All right, seems not. Yeah, thank you, Alain, and thank you all for coming, whether in person or online. And yeah, see you soon then. Thank you. Bye-bye.
Thank you.